Welcome back. We now know how to balance redox reactions. And if you remember from the last video, every time I wanted to say redox reaction, I kept saying electrochemical reactions, because the point of this chapter is not just the redox reactions. The point of this chapter is to use those redox reactions to do something useful, which is electrochemistry. So that's what we're going to talk about now. How do we actually take those redox reactions, do something useful with them, and make stuff do things? So you can see a picture that I've got here is what we would maybe call a very stereotypical lemon battery. You've probably seen this before. You may have even done an experiment before. You generally take a nail and a penny, you put them in here, you connect them with things, and you might be able to light up a little LED bulb, or they used to try to do it with light bulbs. It was a little harder. And so you can do these things. You can make light. And as a kid, as someone who didn't know a whole lot of chemistry, you always wondered, well, what's the purpose of that lemon? Why lemon? Would orange work? Or is it just lemons? Is there something special about the lemon? We'll get to that in just a moment. So you've seen that before, but how do we actually do that? So what this thing's doing, right, is it's taking some sort of oxidation reduction reaction, and it's actually harnessing the energy of that reaction, right? How does an LED light up? You put electrons through it with enough energy, and it lights up. And so how is it harnessing that energy, right? We know from the thing we did at the very beginning of this that Sn2+ gives away 2 electrons, one here, and our Cerium 4+ is taking those electrons, right? So what we want to do is we want to be able to harness those electrons. And so we need those electrons to move along in a way where we can do something to them, where we can interrupt them and say, hey, I know you're spontaneously going in this direction, but since you're going in this direction anyway, can you carry my groceries? Okay, that's what we want to do to the electrons. So how are we going to do that? How do we interrupt the flow or maybe carry the flow of electrons? We do it with wires. You see all the wires in that diagram there? That's how we do it. So you might think at first, well, how would if I take a beaker and I put some Sn2+ into it? I put the tin in there, and I put my cerium in here. And then all I'm going to do is I'm just going to connect these two by a lovely copper wire. So I'm just going to connect them. And what's going to want to happen is that tin, I'm telling you, it's a spontaneous reaction. So that tin is going to want to spontaneously give away electrons and send them over to the cerium, who is happy to accept them. And if you put them in the same beaker together, that would absolutely happen. That reaction would happen automatically. You wouldn't have to do anything. It's spontaneous. And in fact, even in this scenario, that reaction will happen spontaneously for like a nanosecond. Why only a nanosecond? Well, let's look what happens. If Sn2+ is transferring electrons over here, so we're saying, hey, my electrons are flowing in this direction. What happens after a very short period of time? Well, there is some chemistry that happens, so it's not exactly this. Essentially, I'm building up a negative charge on the right-hand side, right? And what am I doing? I'm leaving behind positive holes on the left-hand side, and that's not really sustainable, right? Because as I build up that electron, it doesn't take long before that one has enough of a negative charge on it to repel the electrons that are trying to go that way, right? Like signs repel. And so we can't just do that, because eventually these guys will repel the other electrons, and the plus signs will pull the other electrons back. And so you might get this little tiny instantaneous current, a very, very small amount, but then it would just stop and nothing would happen. What we need is we need a way of balancing. As we're putting those electrons one direction, we need to make sure that we're balancing charge by putting positive ions the other way. How do we move positive ions? We only know how to move electrons. Well, it turns out what people use is something called a salt bridge. And a salt bridge is, in a cell that you might make in a lab, is a piece of glass that's filled with a solvent, oftentimes, but not requiring, potassium nitrate. And that solvent is connected to your cells, but not spilling into it. So usually there's some sort of filter there where, stuff can filter through over time, but it's a relatively small flow rate, but it is electrically connected. Because if you remember, electricity is the movement of charge. It's not specifically and only the movement of electrons. It's the movement of any charge is electricity. Mostly we do electrons because we're harnessing it through wires in our home. But notice there's wires going in your home, and there's also wires going out of your home, because you don't want to be storing all those extra electrons. So this salt bridge, what it does is, as our electrons flow this direction here, and we start to have electrons over here, what do we need to do? We need to balance those electrons out with some positive charges. So what happens is some potassium starts to flow in this direction to help balance out the charge on my beaker on the right. I left some positive holes over here, right, by taking away electrons. And so what happens is some nitrate ion migrates that direction to fill out some of the holes that we are left behind by migrating our electrons. And now all of a sudden, we've got this way of balancing things out, and this electron flow can just keep happening because it's spontaneous. And that's what will happen. You connect those two by a wire and a salt bridge, and the electrons will just flow and flow and flow and flow. But what do? We break this, and we put in our phone. And we say, hey, no, I don't want you to just flow that direction. I'm going to just make you do a few things before you get to go over there. And they're like, okay, as long as you don't make us do too much, right? It's like if you're asking kids to do some chores, it might be okay, but don't ask them to do too many chores. Okay, spontaneously, they want to go get ice cream, but if you tell them they have to replace all the flooring in the house before they go to ice cream, that's just a little too much. Okay, so same thing here. You can tell them to do some, but not too much. What's some? What's not too much? We'll get into that later when we actually calculate the energies of these things. But suffice it to say, if you don't tell it to do too much, then on its way, it'll use a little bit of its energy in order to do something useful for you. Okay? That's how we harness the energy. But you have to have that salt bridge. You have to have that way of balancing out the charge so you're not just building up electrons as you go one direction. All right, so cells like this that operate spontaneously, all we need to do is connect them and they go ping. Those are called galvanic cells. So a galvanic cell is the same meaning as spontaneous. And if you're a few steps ahead of me, you're like, spontaneous. We know about spontaneous. We know how to calculate spontaneity, and we will. We'll calculate the spontaneity of cells and see how we can predict it. So galvanic equals spontaneous. Galvanic is also equal to voltaic. Okay, these are just synonyms. A galvanic cell, voltaic cell, they are synonyms. They mean the same thing. In this particular picture, they decided to use a voltaic cell as their thing. I tend to say galvanic cell. Neither one is good or bad. They're both the same. All right, so let's look at the parts of a galvanic cell, of a spontaneous cell. We have those two beakers that I just drew in the last one on the left, one on the right. They have solutions in them, and they're connected by this thing, which is our salt bridge. Again, you can see in this one they chose potassium nitrate. And you can see our electrons are flowing in this direction, and we harness them in the middle and say, hey, do something useful for us as you're going over that direction. They say, fine. So what's happening? Well, this is a redox reaction, right? So somewhere something's got to be reducing, and somewhere something's got to be oxidizing. So let's look on the left-hand side. They drew this lovely little picture for us as a blow-up of what's happening on this little piece of zinc that they put in on the left-hand side in a solution of zinc nitrate. So what's happening is they're saying 2 electrons are lost by each zinc atom when they're oxidized. And so what's happening is you are actually removing solid zinc from the surface of that metal, and you are turning it into zinc ions. Zinc is spontaneously oxidizing, right? Loss of electrons is oxidation. Zinc is spontaneously oxidizing, losing electrons, becoming ions in solution. So if you start off with 1 molar zinc nitrate, later on you're going to have something slightly higher in concentration in zinc because it's actually being created as this cell runs spontaneously. On the right-hand side, what's happening is the opposite. The electrons are coming over there. You've got lots of extra electrons coming over. Those extra electrons need somewhere to go. So the copper from the solution, the CO2 plus in solution, is actually adding 2 electrons to become copper solid. You have that reaction down here again. And that's a reduction, right? When we're adding electrons, we call that a reduction. We're reducing the oxidation state from +2 to 0. And so if you actually waited long enough, you could actually see that copper electrode get bigger over time. It's adding to its mass. Where does it get that copper from? It's in a solution of copper to nitrate. Okay? It wouldn't work quite as well if it was in a solution of zinc nitrate because there wouldn't be copper to plate on there. All right, so that's what's happening. We've got one side of this cell is oxidation, one side of this cell is reduction. So we've essentially taken a redox reaction and split them into half cells, which is one of the other reasons we write half cell reactions, is because that's actually what we can do in the physical world. We can actually separate these connected by a wire on a salt bridge and have the chemistry of each half cell happen kind of on its own, but obviously requiring the other one and those electrons that flow. So as a convention, people will always draw the oxidation on the left. Now, by always, I mean almost always. Okay? It's not a like, thou shalt, you must, but people get confused when you don't. But it's something to pay attention to, okay? When you're drawing them, I want you to draw them with the oxidation on the left. The thing that's being oxidized should be on the left-hand side. The thing that's being reduced should be on the right-hand side. But you will occasionally see them where it's opposite. Not common, but maybe, some examples coming up soon. Okay, you're going to see that. So oxidation on the left, reduction on the right. Also, another bit of language that you need to know is the thing that's being oxidized we call the anode. In this case, the zinc is being oxidized. Zinc is turning into zinc 2+. It's being oxidized. We call that the anode. The thing that's being reduced we call the cathode. Anode, oxidation, cathode is reduction. How I remember them is these are both vowels, these are both consonants. If you look on the web, there's tons of mnemonics that people have. That's how I remember it. Both vowels, both consonants. Anode is oxidation, cathode is reduction. So that's what I do. So you need to know those. You need to be familiar with those. If I say, oh, the anode, you should know pretty quickly that, oh, that's where oxidation is occurring. If I say the cathode, oh, yeah, that's where reduction is occurring. Line notation, okay? Do we have to draw these like beakers with lines and things like that every single time we want to talk about an electrochemical cell? The answer is no, we don't need to. There are shorthands that people have developed over time in order to talk about those. So again, we're going to draw our two little beakers here. We're going to draw a line connecting them. We're going to draw a salt bridge connecting them. And then we've got some solutions in here. And again, we do mostly in solution here because that's some of the easier chemistry. We'll see a lot of battery chemistry later on that's not in solution. That is solid chemistry, which is kind of neat. Like, wait, we need things to move. How do things move in a solid? Wait. All right. Remember what's on the left? Anode. Oxidation. How do we know it's anode? Comes first in the alphabet. And this is the cathode. Anode is where oxidation, cathode is where reduction takes place. So what we do is we have a general system here. We're going to draw it like this. Let's use the same system we had last time. We're going to have the zinc here. We're going to have the zinc 2+ in solution here. And we're going to have our copper here. And we're going to have our copper 2+ in solution here. And you're like, Professor Clements, no, there wasn't copper 2+ in solution and zinc 2+ in solution. There was zinc nitrate in solution and copper nitrate in solution. Professor, can you please write that properly? But remember, when we write zinc nitrate, aqueous, what do we mean? Right? It's just a shorthand. Is there any zinc nitrate in that solution? No, zinc nitrate is 100% soluble. There's no zinc nitrate in that solution. There are zinc ions and there are nitrate ions completely separated from each other, all surrounded by water molecules, not talking to each other. And so when I say, hey, I've got zinc ions in solution, that's exactly what I have. Okay? So I've got zinc ions in solution, I've got copper ions in solution, even though in the last one they called it zinc nitrate and copper 2 nitrate. That's not what's actually there, but it is a shorthand that's a common use. All right, so we've got the anode on the left, the oxidation on the right. So what we're going to do is there's a notation that we use called line notation. It's got several parts, and we'll go through it as we develop this example. So the first thing we're going to do is we're going to write out each reaction using each half cell, using the line notation. So what you do is you do things in order that they happen. So zinc is being oxidized, which means we know that zinc solid is turning into zinc 2+. So I'm going to write them in that order, zinc solid turning into zinc 2+, right? And I'm going to put phases on everybody. And then how I separate phases is with a single line. Okay? This is why it's called line notation. So I separate those two phases using that line, but the order is important. It's telling me that the zinc solid is turning into zinc 2 plus, not the other way around. On the cathode side, what do I know? I know that copper 2 plus aqueous is turning into copper solid. How am I going to separate those two? Phase separation is that single line, right? So that single line, let me just put there, is a phase separation. We'll see in a moment that when we have two things in the same phase, we separate them with a comma. Okay, so we've got our phase separation there, copper aqueous turning into copper solid. As a convention, just like I said, when we draw it, we almost always draw the anode on the left. In line notation, it is a thou shalt. You must put the anode on the left, cathode on the right, alphabetical, anode, cathode. Okay, and oxidation reduction is also the same, right? It's the same alphabetical. So you must do it alphabetically, anode before cathode. And then to separate the anode and the cathode, what do we have? We have a wire and a salt bridge. And a salt bridge is two lines. And so I separate the anode and the cathode by the salt bridge. And it turns out this very compact notation tells me exactly what's happening in that cell. It doesn't tell me absolutely everything. It doesn't tell me that my zinc 2 plus is a zinc nitrate solution versus a zinc sulfate solution versus a zinc chloride solution. It doesn't tell me that. But it tells me the important chemistry. It's very similar to net ionic reactions, right? The stuff that's actually doing the chemistry goes into the line notation. The stuff that's not doing any chemistry does not go into the line notation. So we know that on the left, zinc is turning into zinc 2 plus in my anode, and we know on the right, copper 2 plus is turning into copper in my cathode. Always read from left to right in line notation. All right, so that's pretty easy. We had that one, but let's do our one from the very beginning here, where we had our tin and our cerium. If you remember, tin was being oxidized. It was losing its electrons. Where does that go? Is that on the left or on the right? Hopefully you came up with the left because it's being oxidized. So we're going to put our tin 2 plus in here. We're going to put our cerium 4 plus in here. Now, if you remember, the balanced reaction had two ceriums, one tin, making one tin 4 plus and two cerium 3 pluses with phases, right? So I should put aqueous on each one of these. And I point that out because what you'll find in the line notation that we're about to do is we're not going to put any of those 2s or 1s or anything like that. Line notation does not, does not have stoichiometry. It has the chemistry, but not the stoichiometry. We know we need to connect this by a salt bridge, and we know we need to connect it by a wire. So we've got these solutions here, and we've got to connect it by a wire. Now that's interesting. Can I just stick the wire in the water? And, you kind of could, but it turns out that wire is generally made of copper. Now, copper is going to undergo its own chemistry with tin on this side. If I just put a copper wire in there, there's some other electrochemistry that can occur there. On the right-hand side, if I just put a copper wire in there, there's some other electrochemistry that can occur with the cerium. And so what would happen is I'd end up with a little battery system that wasn't just tin and cerium. It was tin and cerium and tin and copper and cerium. And you'd have to take into account all of those and blow your mind. It's really hard to do. So people don't do that. What they do is the stuff they dip into the solution, they want to make sure it's either something that's directly participating in the chemistry, which is what we had up here. The zinc was directly appearing in the chemistry, so we can just stick zinc metal in there, and great, it conducts electricity, it's doing the work for us, and that's fine. On the other side, copper was participating in the chemistry, so we could just put solid copper in there. It was doing what we wanted it to do. Here, we can't do that as easily. Now, could we make a tin electrode? Probably, but what would happen? That's tin solid. Tin solid isn't a part of our chemistry here, and so we would actually have another set of chemistry here. So what do we need? We need an electrode, right? Something to put in solution, to get those electrons out of solution and put them into our wire that's not going to react with anything. That's not going to participate in the chemistry. And there's a few ones that people like to choose. The most common by far is a graphite electrode. So literally pencil lead. Pencil lead is graphite, and literally you can actually, shave everything off a pencil and use a pencil. In fact, some people don't even shave off the pencil. You'll see things on the internet where people just connect electrodes to the top and the top half and the bottom half of a pencil, and they can do some electrochemistry using that. The second most common is platinum. Platinum is very non-reactive, and so you can put it in just about any solution and nothing will happen. Why is graphite much more common than platinum? Is cost. Graphite is ridiculously cheap. Platinum is ridiculously expensive, so you only use it when you really, really need to, when it's really important that your electrode is really, really good. It's a better electrode. Some people will use gold. You'll find gold electrodes. However, gold does undergo some electrochemistry, so you have to be more careful with gold electrodes or silver electrodes, things like that. They do undergo enough electrochemistry that you have to be careful with them. In fact, silver I wouldn't recommend at all. So those are our two most common, what we call inert electrodes. They don't do any chemistry. You will have times when you need to use an inert electrode and I don't tell you. So in those cases, you can pick either carbon graphite or platinum. I don't care which, as long as you have an inert electrode. So what we're going to do is we're feeling rich today, so we're going to put some platinum electrodes on both sides. Now remember, the platinum's not participating in chemistry, so it doesn't really matter that it's on both sides. Okay? It's just there as a conduit so those electrons can go from the tin over to the cerium out of the solution without creating another battery there. Excuse me. So what do we have here? Well, we have the same thing, right? We know that tin 2 plus on our anode side, right? Anode oxidation is going to tin 4 plus. Both of those are in solution. So it might be tempting to draw our little bing there, but remember this guy's aqueous and this guy's aqueous, and our little line here says I've got a new phase, but I don't have a new phase, and so I just put a comma. The left to right order still matters. It's still tin 2 plus going to tin 4 plus, but since they're in the same phase, I put a comma there. What's happening on the other side? I've got my cerium 4 plus aqueous going to cerium 3 plus aqueous, and I put a comma between those as well because they are in the same phase. I put my salt bridge in the middle there, and you might be like, hey, I've got something done here. But it turns out, because we're using an inert electrode, that's an important part of how to set this thing up. If you didn't tell someone that, they'd be like, wait, how did the electrons get out of that solution? So when we use inert electrodes, those also need to go into our thing, and they always go on the outside. So the inert electrode's always going to be on the furthest out parts of your line notation. It is in a different phase, so I'm going to go ahead and put my single bar there to indicate that it's in a single phase. If it was in graphite, you just put CGR there instead of PTS. Right? And now this is the line notation for our tin and our cerium. Again, even though the cerium has a 2 factor in the stoichiometry of the balanced chemical reaction, we don't put that factor into our line notation. We just say, look, on the left, we're using a platinum electrode to turn tin 2 plus to tin 4 plus. On the right, on the cathode, we're turning cerium 4 plus into cerium 3 plus using a platinum electrode. Right, so that is our line notation. Occasionally, when we balance our things, we're going to end up with things like H plus. We saw some examples where we're balancing H plus. That does go into line notation. So if you see H plus in your balanced things, you should put that in there. The location doesn't matter too much, but if it's on the left-hand side of the reaction, it should certainly go before what's on the right-hand side. So for example, it's not the case, but for example, if my tin 2 plus had some H on the left, I'd put comma H, comma here with my aqueous, right? But if it was appearing on the right, I generally put it after the tin. It doesn't matter too much. There's not a strong convention that I know of for that, but that's the way you want to do it. H2O does not go into your line notation. So if you balance something with H2O, don't do it. If you balance something with OH and basic solution, that would also go into your line notation. All right. But again, making sure comma separates things in the same phase, line separate things in different phases. All right, so that is our introduction to phase notation, and now you get to try. Okay, which line notation is the correct for a cell that converts Fe2 plus to Fe solid using manganese? Go! I can't see you. Where'd you go? You're going. Oh, there you are. Peekaboo. All right. What did we figure out? Well, we know that Fe2 plus is going to Fe solid. Is that an oxidation or is that a reduction? Well, I look at that and say, well, it's gaining electrons. That must be a reduction. That means it's going to appear on the right-hand side of my line notation, because things that are oxidized at the anode appear on the left. Things that are reduced at the cathode are on the right. And so I know immediately, ping, ping, it's not going to be that one. So if my iron was reduced, that must mean my manganese was oxidized. So oxidation is loss of electrons. So I must be going from solid to +2. How do I know it was +2? Because the answers told me that. All the answers had +2 in solid. I didn't know that off the top of my head, but since every single possible answer was all just +2 in solid, you could kind of figure that out. I wouldn't ask you, without some other information that we'll get to later on, I wouldn't ask you to figure out, oh, is the manganese going to +4? Is it going to +5? Are you going from +3 to +2? I wouldn't ask you any of that. But in this case, since it was given, we can assume it. So MnS goes to Mn2 plus, so we have to write it in that order, right? Because the oxidation is happening in that order, which tells me that it must be this guy here. All right. Another one, what's the proper line notation for the cell that is drawn below? There is a sign there that says, pay particular attention to which way the electrons are going. So I would recommend that you pay particular attention to which way the electrons are going. All right, what'd you come up with? Well, if my electrons are going this way, that means the oxidation is happening over here, and this is actually my anode. That means this must be reduction, and this is my cathode. So you have to be careful with that. So if I've got oxidation and I've got Pb and Pb2 plus, that's going to be Pb going to Pb2 plus. If I've got reduction and I've got silver and silver, that's going to be Ag plus going to Ag. Again, how did I know that so quickly? Well, oxidation is loss of electrons. So I knew that on the right-hand side, something had to be losing electrons. When I looked there, I'm like, well, what's going to lose electrons? Nitrate? Nitrate never does anything. As soon as you see nitrate, you disregard it. Like, I don't even see nitrate anymore. I have to remember to see nitrate so I can tell you guys not to see nitrate. So what's going to lose electrons? Probably lead. Metals do most of the electrochemistry in the batteries that we talk about. So if you're really trying to figure out what to focus on the metals first. If that doesn't work, then you can focus on something else. So I knew something had to be losing electrons. Lead must be going to lead 2 plus. Why? Because those are the species that were present in my beaker. On the left-hand side, I knew that was reduction. Something was gaining electrons. So my two species present were silver and silver plus, so I know it had to be silver plus going to silver. Now, even though I drew this one with reduction on the left, oxidation on the right, in line notation I must have oxidation on the left. So on the left, I'm going to have Pb going to Pb plus 2. Right? This one or this one? Which one is it? It's in order. So I can't be that one because that says Pb plus 2 is going to Pb. And on the right-hand side, I've got the Ag plus going to Ag solid. And that matches what I'm doing. And the answer here is B. All right, last one. What's the proper line notation for this cell? Let me blow it up. Well, I can't blow it up too much because you need to be able to see the answers there. What's the proper line notation for this cell? Notice the electrons are flowing to the right. What did you come up with? Well, we know that oxidation is occurring here because it told us that the magnesium is turning into magnesium 2 plus. So I need something where magnesium is turning into magnesium 2 plus in my oxidation, my anode, which always happens on the left. So I know it's not that one. I know it's not that one. On the third one, magnesium 2 plus is turning into magnesium, and that's not what we have. So it must be the first one, but let's figure out the rest of it. So I've got magnesium turning to magnesium 2 plus. Great. On the other half, I'm going to have to shrink this down a little bit so I can show it to you. I've got VO2 plus going to VO2 plus. You got to say those funny, right? VO2 plus coming to VO2 plus. There's some H, right? We put the H in there. Again, I didn't even follow the notation I told you earlier, which was that the H should go in the middle, because it's not really a strict thing. It just says, hey, this is an acidic solution. You need to make sure you've got acidic solution there. Okay, so I've got VO2 plus going to VO2 plus. I had a platinum electrode. Why do I have a platinum electrode? Because I didn't have a metal on this one. I didn't have a metal that was participating in the reaction. So my answer here is A, which we could have just figured out from the magnesium, but let's say you had to write the whole thing, you would have had to figure out the other things that were going on. All right, so we now know line notation. We know a little bit about the language, the anode, the cathode, where to draw them, how to put them in line notation, and right, we could also use that line notation and extract back out something about the chemical reaction. So if I had line notation that said magnesium solid goes to magnesium 2 plus, you'd be like, okay, that's my anode, right, drawn on the left. Magnesium solid is my electrode because it's this metal. I need something to conduct electricity. That's got to be my electrode. And I've got magnesium 2 plus in solution. So you can figure all those things out from the line notation, or we can start with the things figured out and write the line notation. Thanks so much for listening. Have a great and wonderful day.